There's, I think, 8 in the series of lectures. So I think last time I started with finding definition of convolution. I couldn't complete it, so let me continue with that. So, so if f and g are two functions, their convolution is a function which is defined like this: f star of g. F and g are two functions of variable t, independent variable t. F star g is another function. It's a new function. New function means I have to tell you what are its values at different values of t. T is again the running variable. So f star g of t I have to tell you. So here is the definition. F star g of t is f of t minus u into g of u du. Integrate this from 0 to t. Take 2 minutes to understand the definition. For example, if f and g are two functions, now f star g is another function which function in t. That means, for example, I want to find what is f star g of 1. F star g of 1 is 0 to 1 integral of f of 1 minus u into g of u du. So I integrate this with respect to u and I'll end up with t, and that I'll integrate from 0 to t, 0 to 1, because I want f star g at 1. If I want f star g at 2, then I'll do the same thing with t replaced by 2. So for every point, if I want to find the what is value of f star u, I have to keep integrating this and limits between 0 to whichever point I want. That's the definition of convolution. Yeah, a priori it looks pretty weird and very convolved. That's why it's called convoluted. It looks very artificial, but it isn't very artificial. Let me tell you that. Uh, Sounds like that. So it takes some time to understand this definition properly. Take your time, no hurry. Let me repeat. So f and g are two functions of t, and I want to define a new way of combining f and g. For example, we have seen different ways of combining f and g. We have seen how, what does it mean to say f plus g. For example, f of t is t and g of t is t square. What is f plus g? So f plus g is another function which I have to tell you its value at various values. So for example, f of g of 1 is f of 1 plus g of 1. F of 2 is, sorry, f plus g of 2 is f of 2 plus g of 2. Like this, at various points, I can find out what is f of f at that point and g of at that point and add them, and I tell that is the value of f plus g. That is how I define f plus g. Similarly, f minus g, f into g, f by g when g is not 0. All these things we have seen before, playing around with functions. So this is a new way of combining two functions. F star g is a function of the independent variable t. How is it defined? In a pretty involved way, the way you see it on your screen here. F star g is f of t minus u, g of u integral of this between 0 and t. Of course, integration is with respect to u. Don't ask me where did this u come from. This is basically you are integrating with respect to u. G, running variable of g is u in this integration. So that's what I was explaining. This is a new way of combining two functions which give rise to a function in T. Now, in this course, we won't be interested too much in the geometry of convolution. This convolution is a very important operation. It's a new operation for you. First time probably you are seeing it. It has a lot of applications in engineering. It basically tells how, for example, if f and g are two signals, convolution of signals is important to study. It's important to study how they come together, how two signals come together. So this is one way of putting two signals together, convolution. We won't be interested too much in the geometry. Maybe depending on your branch, you will learn it sometime in your departmental courses. But here, I'm interested in finding, there is a theorem of how Laplace transform relates to convolution. So I want to explain that. That's all the goal in this section is. So let me So I won't go into geometry of convolution. Instead, I'll just give you a very brief example of what convolution means. For example, let us take convolution of these two functions. F of t is t and g of t is t square. Let's see what happens if I convolve these two. Convolve means, as I'll repeat it, it means just combining two functions with a different rule, with a particular kind of rule which I just explained to you. For example, if f of t is t and g of t is t, f plus g is nothing but t plus t square. F minus g is t minus t square. F into g is t into t square, which is t cubed. F by t is t by t square, which is 1 by t if t is not 0. Otherwise, it's not defined at that point. So these are ways of combining f and g. Like this, we are trying to combine in yet another way, and I'll call that convolution. So let's see what happens to these when I convolve these two functions. What is the result? I'll try to see. So definition of f star g at t. F star g, remember, it's a function. So I have to tell you what is its value at different values of t. So f star g of t by definition is f of t minus u g of u du, integral of this from 0 to t. So f of t minus u, so here f of t is t and g of t is t square. So what here f star g is integral of f of t minus u g of u du. Now what are the f of t minus u? If f of t is t, f of t minus u is t minus u. And what is g of u? G of u is u square. So I get t minus u into u square. I have to integrate that. T minus u into u square, integrate with respect to u between, and I want it between limits 0 and t. So this is an easy integration. I'll get first t u square minus u cube. T u square, if you integrate with respect to u, you will get t u cube by 3 minus u cube. If you integrate, you will get u power 4 by 4. That's what I have written here. So if you integrate this, you get t u square, you integrate, you will get t u cube by 3, and u cube, this u cube you integrate, you will get u power 4 by 4, and whole thing between the limits 0 and t. Remember, this is u which is varying from 0 to t, because it's that variable with respect to whom I am integrating this function. Okay, so to evaluate this, I'm sure you can all do that. This is 1 by 12 t power 4. Both are right. This is t power 4 by 3 minus t power 4 by 4, and at u equal to 0, both become 0. So I get 1 by 12 t power 4. So the upshot is, this process is one thing. This is the process through which explains to me how do I convolve two functions, how do I combine two functions. The upshot is, if ft is t and gt is t square, then f star g is 1 by 12 t power 4. This is a new function coming from, so you can see geometrically it's really doesn't seem to have much relationship. This is a polynomial of degree 1, this is polynomial of degree 2, whereas this is polynomial of degree 4, and coefficients doesn't seem to have a nice connection. Here coefficient of t is 1, here coefficient of t square is 1, but here suddenly coefficient of t power 4 is 1 by 12. So how did it come? That it's come because of convolution, but it's not very clear or straightforward. For example, f plus g is 1 plus t square. That was very easily seen. So this is also easy, but it will involve a bit of work. That's all. So this is what convolution means. I won't go too much into geometry, but just to give you a feel of it, I will show you. I'll plot these three curves and show you. This is one more notation before I go about plotting. I won't keep writing its f star g of t. This t will, I'll eat it up. I will keep just writing f star g is equal to t power 4 by 12. I won't say, even though f star g is a function or independent variable t, I won't keep mentioning that. I just write f star g is t power 4 by 12. That means you have to understand that this is a function whose running variable is t, and the value of this function or the expression for this function is t power 4 by 12. All this goes unsaid. So we won't keep writing f star g of t, but I just written it just initially so that you get used to the fact that f star g is a new function of t. That's all. Afterwards, we won't keep writing. So we just say f star g is t power 4 by 12 in this case. So let us see the graph, how they look. So if ft, I'm trying to convolve this ft and gt. So ft, also, I know how the graph looks like. Ft is t. This is a straight line passing through the origin with slope 1. And gt equal to t square is nothing but a parabola. So this is the these are the two curves which I am trying to convolve. What I get is 1 by 12 t power 4, which looks like this. So it's not clear. You see, how are these things related? How do I know when I do this, when I convolve this and this, I'll get this? Geometrically doesn't seem to be clear a priori, but I won't bother about it since this geometry of this convolution is not in your course. I won't uh, deal more about it, but you should know how to find convolution of two functions. That's an important operation. And just to tell you that it is it's easy, but just to tell you that it is indeed involved, I am showing you these examples where both the functions which I am convolving are very easy, simple functions, ft equal to t and gt equal to t square. But their convolution turns out to be 1 by 12 t power 4. You should try using some of these graphing calculators and integration to convolve sine and cos, or even a polynomial with sine and things like that. Try seeing what happens. Interesting exercises. Anyway, you have to do, especially if you are in ECE or electrical, sometime later in your course, if not this semester, in some core signals and systems somewhere, you will learn how to convolve signals. So for me, what is important in this course is convolution theorem for Laplace transform. This is the most important thing for us, and this is a very powerful way of using Laplace transforms to do various things. I'll show you illustration. That part illustration of all these things is in the last part where I show you how to solve differential equations. But till then you have to bear with me. So this is a very powerful method, powerful to find Laplace transforms, inverse Laplace transforms, and things like that. So the statement of convolution theorem for Laplace transform is the following. Laplace of f star g is Laplace of f into Laplace of g. Please note the simplicity and beauty of this equation. This says Laplace of the convolution of two functions is product of Laplace of functions. So take f and g, f star and g star, f and g, and take star their star. That means if I convolve them, then take Laplace. That is same thing as taking product of Laplaces of both the functions. So what it essentially says is Laplace respects convolution as a product. You see that what you should keep in mind here is L of f into g is not LF into LG. It's like differentiation. D of f into g is not df into dg. D is differentiation. D of, you must have, if not fg, you must have heard of it as uv. D of uv is not du into dv. Instead, it is du into v plus u into dv. You know the uv rules for product. Correct? So Laplace is also something like that. What is Laplace of f and g? I don't know what it is. It's not so simple, straightforward. But so basically Laplace doesn't respect products. That means L of f into g is not LF into LG. Whereas L of f plus g is LF plus LG. That we have seen, it's a linear operator. Similarly, differentiation also respects addition. That means d of f plus g is same as df plus dg. L of f plus g is LF plus LG. But L of f into g is not LF into LG. So the next question could occur. What is L of f into g? That I don't have a formula here now. But I have a formula for what you are expecting L of f into g to be. You want L of f into g to be LF into LG. It is not true. But if you want LF into LG, I can tell you how you must combine the functions. That is the crux of this theorem. It says Laplace of f star g is LF into LG. P you can forget, it doesn't matter. P is always, in Laplace transforms, we always use P as the time domain, which is the independent variable T. So L of f star g is LF into Fg. In our usual notations, L of f star g is capital F into capital G, capital F of S, capital G of S. That's the notation. So essentially, that's what this says. Laplace converts convolution to product. So that means if I have convolution of two functions, you saw how convolution can become very weird. Even simple functions like t and t square, the convolution became t power 4, 1 by 20 power 4. So a priori, it's not clear that what is, how do I find Laplace of f star g? But this theorem says it's very easy. All you have to do is take Laplace of each function and multiply them. For example, let us do this orally. I don't think I've done this, worked out this problem in your course. I have not put it up on the PPT, but let's see this. Let us see what is f star g. I know it is this. What is L of f star g? That means Laplace of this function is, you take Laplace of t power 4 by 12, which is 1 by 12 into Laplace of t power 4. I have not made the PPT, so I am telling you orally. So Laplace of f star g is Laplace of t power 4 by 12, which is 1 by 12 into Laplace of t power 4. Laplace of t power 4 is what? Laplace of t power n is n factorial divided by s to the power of n plus 1. So that will be t to the power 4 factorial divided by s to the power of 5. So 12 was already, so 4 factorial by 12. 4 into 3 gets cancelled. So numerator I'll have 2. So 2 divided by s to the power of 5 is what I'll get here. Laplace of f star g is 2 divided by s to the power of 5. Now Laplace of f is 1 by s square and Laplace of t square is 2 by s cube. Multiply them, I'll do the same thing here, 2 by s power 5. So what this convolution theorem says is, if you take two functions, Laplace of the convolution is same as product of the Laplace of the functions. This is a very easy verifiable orally, this because we have two just simple straightforward polynomials, easy ones. Now I want to tell you, I want to show some more complicated problems based around this. So yeah, even the proof is not in your syllabus and we'll skip it. The proof of Laplace convolution theorem is not there in your syllabus, so I'll not bother about writing down the proof. It's not very difficult, but I'll not bother about it. What is there instead in your syllabus is to verify this theorem for specific functions. So let us see that. Yeah, so let me check if it's there, so no problem. Yeah. So we will verify Laplace convolution theorem for simple functions, not as simple as two polynomials, slightly more complicated ones. So here it is. This is how typically a question in your examination will come. Verify convolution theorem for functions ft equal to t and gt equal to e power t. That means these are the two given functions, ft is t and gt of t. I want to verify the convolution theorem for these two functions. That means what? First I'll have to find what is Laplace of f. I want to find Laplace of g. Both are pretty straightforward. L of ft is 1 by s square. Laplace of ft is 1 by s square. Similarly, Laplace of gt is 1 by s minus 1 because gt is e power t. We have seen that Laplace of e power at is 1 by s minus a. So here a is 1. So Laplace of this is this. Laplace of t is 1 by s square. Laplace of e power t is 1 by s minus 1. Okay. Hence their product, Laplace ft into Laplace gt is 1 by s square minus s square into s minus 1. Note, I am not taking Laplace of f into g. F into g would be t e power t. Its Laplace is different. I am not saying that is related to this. In fact, what is Laplace of t into e power t? You remember, we have done this kind of thing. If you multiply by e power at, it's like taking that out is a 1 by s minus a. So Laplace of t is 1 by s square So Laplace of e power t into t is 1 by s minus 1 whole square. That has nothing to do with Laplace of f into Laplace of g. They are not equal. This is what I wanted to illustrate also. See, Laplace of f into Laplace of g is not Laplace of f into g. That is easily seen in this example. Because Laplace of f into g, I have not written it here, is t into Laplace of t into e power t is nothing but 1 by s minus 1 whole square, which is nothing to do with 1 by s square into s minus 1, which is Laplace of f into Laplace of g. Instead, we will see what is f star g. That means we will see what are the convolution of these two. So by definition, f star g of t is f of t minus u into g of u du. That means you integrate with respect to u and integration limits between u equal to 0 to t. This is the definition of convolution of these two functions. So let us substitute the values then. I know ft is t and gt is e power t. So f of t minus u is t minus u and g of u is e power u. So I'll get, what am I integrating? I'm integrating t, integrating with respect to u, which function? T minus u into e power u. That's what it is here. T minus u into e power u. Now you break it up into two integrals, t e power u minus u e power u. T e power u is very easily integrable with respect to u. This t is to be treated as constant. I mean, don't think it's not a constant, but it is not a running variable in the integration. So I can take t out. T into integral of e power u is e power u itself. So first term I'll get is t e power u, that is between 0 and t. U is between 0 and t, correct? So you will get e power t minus 1 is what you will get. And similarly, u e power u, no, you won't get that term. You'll have to write down. I have not written down these details here. So please, you integrate t e power u minus u e power u. How will you integrate u e power u? You have to use product formula. Product of, integral of u into v is u into integral of v minus integral of differential of u into integral of v. Integral of first function into second function is first function into integral of second function minus integral of derivative of first function into integral of second function, all with limit 0 to t. So you do it. This is a easy exercise. You must have done these kind of things in your second QC. So t e power u minus u e power u. If you integrate between 0 and t, you will get minus t plus e power t minus 1. And Laplace of f star g is, so this is f star g. So Laplace of f star g is Laplace of e power t minus t minus 1. I just written in such a way that the first term is positive. I mean, yeah, it's positive. I don't want negative right in the beginning, so I pushed it here. E power t minus t minus 1. And what is Laplace of this? Because I use linearity. This is Laplace of e power t minus Laplace of t minus 1, which is nothing but 1 by s minus 1 minus 1 by s square minus 1 by s. Laplace of e power t is 1 by s minus 1. Laplace of t is 1 by s square. Laplace of 1 is 1 by s. So if you simplify this, you will get s square into s minus 1, which is same as Laplace of f into Laplace of g. So I have verified convolution theorem. What does the convolution theorem say? Laplace of f star g is equal to Laplace of f into Laplace of g. And here I have checked that Laplace of f star g is 1 by s square minus s minus 1. And Laplace of f into Laplace of g is 1 by s square into s minus 1. So both are equal. So I have verified convolution theorem. This is typically how you verify convolution theorem. For a given two functions, you have to find Laplace of each of the functions, take the product and keep it. Then you have to compute the convolution. Here is the convolution. Compute the convolution using this definition. So unless you remember the definition of convolution, you won't be able to solve problems of this kind. So this is the convolution. So you should know how to evaluate some very elementary integrals. And then you find Laplace of that. Normally in your exam, the convolution will be something which is not very difficult to find Laplace of. So you should be able to find Laplace of this easily. There it was very simple. T for t and 1. So that's very easy, but it may become a bit more complicated with sine, cos also coming. You must You already know how to find Laplace of such functions. I'll show you one more example where it is slightly more involved. So here it is. It says use convolution theorem to prove Laplace of integral of e power minus u into sine of t minus u du between 0 to t is 1 by s plus 1 into s square plus 1. You see, this is quite means first principles. If you try to do, it's quite a what I would call it as a very khatarnak problem. You see, firstly you have to integrate some horrible function e power minus u into sine of t minus u du. That integration itself is quite scary. And then after integrating, if you can do it by parts or whatever, so you have to do it by parts twice. So you do it. Afterwards, you have to find Laplace of that, which is each one is a non-trivial step. But convolution theorem tells, oh no, I don't have to work so hard, I can do it much easily. How do I do it? You see what this right hand side, it is 1 by s plus 1 into s square plus 1. Observe that I can write this as product of two functions such that inverse Laplace of each of them is easy to find. That means I can write this right hand side as product of Laplaces of two functions very easily. This is 1 by s plus 1 into 1 by s plus 1 into s square plus 1. I can write this as 1 by s plus 1 into 1 by s square plus 1. Why did I do this? 1 by s plus 1, I can write whose Laplace it is. And 1 by s square plus 1, I can write whose Laplace it is. That's what I will do. 1 by s plus 1, Laplace, it is Laplace of g t, sorry, e power minus t. Correct? E power minus t has Laplace 1 by s plus 1. And s square plus 1, it is Laplace of sine t. So what I will do is, of course, I can see that sitting here in this integral. I want to write this integral as convolution of somebody. Then I'm through. So it's easy to see that if I take ft as sine t and gu as e power minus u, what you have here in this bracket is nothing but f star g. I know it requires experience to think like this. That's what your course is all supposed to make you do. So moment I see this, I can see that this is convolution of two functions. One is e power minus u, another is sine of t. How do I know this? Actually, I'm cheating. I don't see that from here. I see that from here. In the right hand side, I have 1 by s plus 1 into 1 by s square plus 1, which is, I can write it as product of two functions. One is 1 by s plus 1, another is 1 by s square plus 1. 1 by s plus 1, I know how to take its inverse Laplace. It's very easy, e power minus u or e power minus t. And 1 by s square plus 1, that is also very easy. Sine t, Laplace of sine t is 1 by s square plus 1. So basically, I am trying to find inverse Laplace of these two functions whose product happens to be the right hand side, and those inverse Laplaces are what I will consider as functions. Ft is sine t and gu is e power minus u. You can take gt equal to e power minus t, it doesn't matter. When you integrate when you take convolution of f and g, you will get f star g, which is the integral of t minus u, f of t minus u into g of u. So f of t minus u is nothing but sine of t minus u. G of u is e power minus u. So their product, and integrate them between 0 to t with respect to u. That is what we have to do. So that means this is nothing but convolution of these two functions. That is what happens. So I'm just showing you the steps, but here I'm cheating a lot. I told you how I know this. One is experience. Number two, how do I get that? By looking at the right hand side as product of Laplaces of two easy functions. That is what I do. That's the crux. You have to see that right hand side is product of Laplaces of two different functions. That is the, if you can observe that, then rest of it is easy. So once you observe that, now you know what are the two functions to take. And I am going to, while writing a problem, solution to the problem, I'll start with let ft be equal to sine t, gu equal to e power minus u. then Laplace of ft is 1 by s square plus 1 and Laplace of g is 1 by s plus 1. So these are the two products which will give me right hand side. So convolution theorem says Laplace of f star g is LF into LG. This is what convolution theorem says. That is true. So what is the L of f star g is nothing but what you see on the left hand side here, because f star g is just this integral of e power minus u sine of t minus u dv. Probably if you write the definition for the first time, you will write it as f star g is integral of sine of f of t minus u into e power u into g of u, which means sine of t minus u into e power minus u, which is same as e power minus u into sine of t minus u. Actually, I have not told here, but it's an important result to be noted. F star g is same as g star f. This star convolution is actually commutative. It doesn't matter which order you commute with. It's very easy. Replace t by t minus u and we'll get the answer. Or will u minus t, doesn't matter. Either way, it's okay. So it is commutative. Whether you convolve f and g or g and f, both are same answers. Anyway, here I written what is f, what is g. So L f star g is, I can see, not I can see, by convolution theorem it is LF into LG. I already computed LF into LG and I see that is equal to right hand side. So left hand side must be L of f star g. So I have found Laplace of f star g, which happens to be 1 by s plus 1 into s square plus 1. So using convolution theorem, I have evaluated Laplace of integral of a horrible function. Finding integral of the function itself is non-trivial. Then finding Laplace of it is even more non-trivial, because that involves another integration. All that I have done very neatly using convolution theorem. Of course, proof of convolution theorem is where you will do all this dirty work, but once you do it, you have it forever. In that sense, convolution theorem is a ready-made statement for you. Using that, Laplace of integral of e power minus u sine t minus u into I proved that this Laplace of this integral is 1 by s plus 1 into 1 by s square plus 1. It's very often for your course the most useful thing. So I have shown you given you illustration of two examples using Laplace, using convolution theorem for Laplace transform. I want to give you more examples, but now it will involve inverse Laplace also. So basically two types of problems you will have in your examination. One is to verify convolution theorem for functions. So given f1, g, two functions, find Laplace of f, find Laplace of g. Find the product of LF and LG and keep it one place. Next, compute f star g, compute the convolution of the two functions, and then find the Laplace of it, and see that Laplace of f star g is same as Laplace of f into Laplace of g. If you can see this, then you have verified convolution theorem for these two functions. Another type of problem is evaluate some Laplace of horrible integral. Now what I will do is I will use, actually we are trying to prove this, so I will use that I'll observe that what is there in the square bracket here. I would like to make it look like convolution of two functions whose Laplaces happen to be, if you take product of their Laplaces, happens to be what is there on the right hand side. So this I have to observe. Given right hand side is product of Laplaces of two functions. Which are the two functions? From this I get sine, and from this I get sine, and from this I get e power minus t. Yeah. So if I take convolution of those two, this is what I get, and hence I have proved Laplace of integral of this is Laplace of f into Laplace of g. So basically I use convolution theorem. These are the two types of problems. Now let me look at this inverse Laplace transform and convolution. That means now I want to use this convolution theorem and taking inverses. Then I'll want to combine something together and show you some easy, nice illustration of application of this problem, this theorem. So convolution theorem, you basically it said Laplace of f star g is Laplace of f into Laplace of g. So I can rewrite Laplace of f as capital F, Laplace of g as capital G. So Laplace of f star g is capital F into capital G, which is same thing as saying inverse Laplace of fs into gs is f star g. F star g is this. Now, what is this useful for? It's the same statement. There's nothing new. Just that you took Laplace inverse everywhere. This, the way it is written here, I can use this probably to compute certain integrals. Because if I know how to take inverse Laplaces, then I know how to find the integral. Or if the finding integral is easy, I can use this statement to find inverse Laplace of some bad functions like fs into gs. So let me show you examples, then it will be clear. So for time being, remember, this is the restatement of convolution theorem, which says Laplace inverse of Laplace of product of two Laplaces is same as convolution of those two functions. That is the statement. I know it's a bit confusing, but written like this, it's not easy. That's the power of right notations. The notation is, you forget about this last integral. Laplace of f star g is Laplace of f into Laplace of g. So instead of Laplace of f, I written capital F. Instead of Laplace of g, I written capital G. So f into g is Laplace of f star g. You take L inverse for the whole thing, I'll get L inverse of f into g is L inverse of L of f star g. L inverse of L is identity, so I'll get f star g. So L inverse of f, capital F into capital G is f star g. F star g by definition is what you see on your screen. So this is a very useful thing. Let me show, instead of doing so much of theory, let me show you an example. Here it is. I want to find inverse Laplace transform of 1 by s into s square plus a square. Yeah, of course I can do this. This is after all a rational algebraic function, and I can use partial fractions and do it. Partial fractions, you see, it's pretty bad method. Bad means it's pretty involved in this. It's hard job. Why? Because there is a quadratic here in the denominator, which I can't factorize because it's like s square plus a square. In real numbers, I can't factorize. Then if I write partial fractions for this, it will be a by s plus bs plus c divided by s square plus a square. Now you have to evaluate all a, b, c and all. It's pretty lot of work. It's correct, one can do it that way. We have probably done this also while I was illustrating to you about how to use partial fractions to find inverse Laplace transform. But here I want to show you a shorter way of doing the same thing. I observe that 1 by s into s square plus a square is product of two Laplace transforms. For example, I can write this as 1 by s into 1 by s square plus a square. 1 by s is Laplace of something very easy, constant function, 1. And 1 by s square plus a square is Laplace of something very easy. It is Laplace of sine, I mean, if you put an a appropriately there, or 1 by a sine t, sine at, sorry, 1 by a sine at. Its Laplace is 1 by s square plus a square. So first step to solve this problem is to recognize this function as product of Laplace transforms of two functions. I hope I'm making sense. This is product of Laplace transforms of two functions. This is 1 by s into s, 1 by s square plus a square. 1 by s is Laplace of constant function 1. 1 by s square plus a square is Laplace of 1 by a sine at. Alright, but 1 by a and sine at and all, I'm sure you can manipulate that now. So that's the first step, is to recognize the given expression as product of Laplace transform of two functions. So here, as I told, 1 by s into s square plus a square is 1 by s into 1 by s square plus a square, which is same as saying Laplace of 1 into Laplace of 1 by a sine at. Because you see here, Laplace of 1 by a sine at is 1 by a into Laplace of sine at. Laplace of sine at is 1 a by s square plus a square. 1 by a is outside, so a and a gets cancelled, so I'll be left with 1. So Laplace of 1 by a sine at is indeed 1 by s square plus a square. Easy manipulation, just using linearity. This means capital F of s, I'll call it 1 by s. Capital G of s, I'll call it 1 by s square plus a square. Then small ft is 1. Small gt is 1 by a sine at. This is just notation for inverse Laplace of capital F and capital G. Now let us see what does my convolution theorem say as far as inverse Laplaces are concerned? It says, remember this, let's go back to the statement. Laplace inverse of f into g is Laplace inverse of capital F into capital G is small f star small g. So that is what I use. Laplace inverse of capital F is 1 by s, capital G 1 by s square plus a square. Laplace inverse of capital F into capital G is small f into small g. Small f is clearly 1, small g is 1 by a sin at. So f star g. What is, by definition, what is this? F star g is integral of f of t minus u gt between 0 to t. You can call with respect to t here. Actually, I should have written u here. I'm sorry. There is a small mistake here, typo. So let me correct this. This is g u du. This is what it is. This is u weighing from 0 to t. That is the definition of Laplace, not Laplace, what is it called? Convolution. So I'm using that. So Laplace inverse of capital F into capital G is small f star small g. This by definition is the integral between u 0 to t f of t minus u into g of u du. But this is nothing but the what happens? Yeah, so this is f of t minus u. Anyway, f of t is constant function. So I just get 1 here. And g of u means 1 by a sine au. If you integrate sine au, you will, between limit 0 and t, then you will get 1 minus cos at, 1 by a square. 1 by a will come out. So you have to carry out this last bit of integration. I have not written down those details here, but I'm sure you can integrate sine at. You will get as cos at by a. So 1 by a was already outside, so 1 by a square will come out. So cos at between the limits 0 and t. So when it is t, I'll get cos at, and when it is 0, I'll get cos 0 as 1. So it should be cos at minus 1. I don't know why it is 1 minus cos at. It's cos at minus 1. 1 by a square, cos at minus 1 is what I get here. Just check the sign. Don't bother too much. Oh no, no, the integral of sine is minus cos. So that is correct. 1 minus cos 80, what I written is correct. So what upshot is, I have found inverse Laplace of this just by integrating this one small easy function. That is by power of observation, that this whatever I want to find inverse Laplace transform of, I can write it as product of two functions whose Laplace transform happen to be this product. That is the observation, and then I use inverse form of convolution theorem. Get this. So this is one power way of finding inverse Laplace transform. This, of course, as I said, I could integration should not become very difficult. If this integration is very difficult, then it is not. Okay. So next, similarly, one wants to find inverse. Here I have two quadratic terms in the denominator, both of which I cannot factorize. A square plus a square I cannot factorize. Then what do? I have to write partial fraction with four constants: as plus b, uh, as plus b divided by a square plus a square. Writing it as partial fractions is not straightforward. So one has to, just 1 minute. writing this as partial fractions is not very simple, straightforward method. So I will use this inverse Laplace transform kind of argument. So let us go ahead doing this. So as a first step, I want to I recognize this as product of two guys, each of which is Laplace of a standard function. That is what we want to do. I want to write this as product of two guys. That's easy here. Here a by s squared plus a square and s by s squared plus a square. If you take their product, I'll get this. A into s divided by s squared plus a square whole square. That's easy. The important point is both these I can find inverse Laplace easily. What is the inverse Laplace of this? Some cos of 80. What is inverse Laplace? Sorry, this is sine 80. And inverse Laplace of this is cos 80. So both inverse Laplaces are easy to find. That's why it's written f of, it's written here. Inverse Laplace of capital F of s is small f, which is sine 80. Inverse Laplace of capital G is small g, which is cos 80. Now what do I do with it? You want to find inverse Laplace of this. That means you want to find inverse Laplace of product of these two, which is nothing but convolution of these two by that convolution theorem. That's precisely what I'm doing. So Laplace inverse of this is Laplace inverse of this into this, which is convolution of f and g. Convolution of f and g means f is sine 80. So f of t minus u, which is f of a into t minus u, into g of u, which is cos of au du. So I carry out this integration, and this integration is not difficult because you know some formula, right? Cos sine a into cos a is nothing but half of sine. I told you these formula are very important for your course. This how to integrate sine into cos, sine into sine, cos into cos, all these things I have told you. This formula you should remember. I hope I have written the formula correctly here. Formula for what? Integral of sine a into cos b is half of integral of sine a plus b plus sine of a minus b. I have written this here. So things will get cancelled, and then I'll get, afterwards, once you write this, integration is very easy because u and u get cancelled here. So I'll get sine 80. And similarly here, nothing will get cancelled here, but it's all a constant. So you integrate, t is a constant here because you are integrating with respect to u. So you should, if you evaluate this, you will get 1 by 2 t sine 80. So this kind of, of course, after doing this, one can check this very easily. What have we done here? We have found inverse Laplace of this to be equal to this. That means Laplace of this must be equal to this. That's easy to see because we have seen this. Laplace of this is, how do I find Laplace of half t sine 80? Half I take it out, and then remaining thing is Laplace of t sine 80. I know how to find Laplace of t sine 80. If you are multiplying by t, I have to basically take Laplace of sine 80, differentiate with respect to s, take negative of it. So you do all that, I'm sure you will get this because Laplace of sine 80 is s by s square plus a square. Its derivative will turn out to be this. You try doing this and minus with the negative sign. So this negative will go away, and I'll get this. To check, cross check this, you will do. This is correct. What I have done is correct. So upshot of this is that this convolution is to be treated with more care, and it's a very fine operation. The beauty of convolution is that Laplace of convolution is product of Laplaces of both the functions. This is an important thing. Using this, we have seen couple of types of problems. One is how to find verify Laplace convolution theorem for two easy functions. That's what we have done here. two functions, find verify convolution theorem means find Laplace of both of them, find the product, find convolution of the two functions, find Laplace of that, and then show that they are equal. That is what this is one kind of problem. Another kind of problem is to find Laplace of bad integrals. Bad integral means a priori it looks pretty pathetic. Integral of e power minus u sine of t minus u du. How do I integrate? But actually I have not integrated this at all, but still I have found the Laplace of this using convolution theorem by just recognizing what is there inside the integral sign as rather including the integral. What is there, whose Laplace I am trying to find is convolution of two functions, and for both the functions I can find Laplaces very easily. That's the main thing. So I observe that this I can write it as convolution of sine t and e power u, e power minus u. So if I mean e power minus t. So when you write convolution, then in the definition t will become u. So convolution of sine t and e power minus t will give me this. So its Laplace is Laplace of sine t into Laplace of e power minus t, which is 1 by s square plus 1 into 1 by s plus 1, which I get this. So this also we have seen. This is pretty easy, straightforward. And another thing which we have seen, these are all important techniques, so I am going slow and then I am trying to recall for you. Another application of this convolution theorem is to find inverse Laplace of some a priori complicated looking function. So all I have to do is restate my convolution theorem using inverses. That is L inverse. So I know L of f star g is capital F into capital G. That means L of f star g is LF into LG. I will take Laplace inverse. Laplace inverse of L of f into L of g is f star g. That's what happens. So at times this may be easy to compute, at times this may be easy to compute. Depending on that, I will either ask you to find this or ask you to find this. Ask you to find this means ask you to find an integral. Then if I know how to find Laplace and inverse Laplace easily, then I am done. Or I might ask you to find inverse Laplace, then integration must be easy. So this is a typical examination kind of question. So let us, we saw examples here. So if I want to find inverse Laplace transform of s into s square plus a square, that means I want to somehow recognize 1 by s into s square plus a square as something here, because then I can find the inverse Laplace easily, which is what we have done, that these are Laplace of two functions which I can very easily find the convolution of. That's what I have done here. Similarly, there is another one. If I want to find inverse Laplace transform of these two functions, but not this function, I write it as product of two functions whose Laplaces are easy to find, which is again I have done here. Here, only thing is I wanted you to see that we are using this formula sin A into cos B is half etc etc sine of A plus B plus sine of A minus B. I hope I am correct. Most probably I am correct in this. And then carry out this integration, usual PUC integration, you will get this answer, which means I have found inverse Laplace transform of this. This completes more or less everything I wanted to say about Laplace transforms, except for one thing, which is how does Laplace transform behave with respect to derivatives. This is the one. If I understand this one point, then I'll be ready to tell you how to solve differential equations. I will let me see. I have 2 minutes, so let me just start this and stop, and in the next class I will continue from here. This is the formula. We have not seen this formula before this, so I will start this, and next class again I will recall this. If I know Laplace, this is like one of the formula which we have seen. We have seen many formula, right? Laplace of t ft, Laplace of t power n ft, Laplace of e power a t ft, Laplace like that. Now I want to tell you one more formula. Laplace of derivative of f, how does it look? If Laplace of f is capital F, Laplace of small f is capital F, how does Laplace of derivative of small f look like? So there's a formula. This is not difficult, it's just straight definition, but I won't spend time on doing this. Not very straightforward because this uses differentiation under integral side, the Leibniz rule of integration. So please go through it sometime if you want to. Otherwise, for your examination purposes, you need to remember this formula. L of f dash t is SL ft minus f0. F0 means value of f at 0. Sometimes it may be 0, it may not be 0. In general, this is the formula. L of f dash t is, that means this basically relates Laplace of the derivative and Laplace of the function itself. That is what this does. So this relationship is important. We will see how to exploit this in the next class. There are some illustrations and there are problems where soon after this we will learn how to solve differential equations using Laplace transform. I think I'll stop here now. Thank you for your attention. We are almost at the end of our course, another 2 classes, I think. Thank you anyway.